dames en here. Dis werklik vir ons 'n voorreg om u te verwelkom by die 2021 Outeniqua Inligtingsdag. Ons het werklik gehoop dat ons vanjaar u op die plaas kon verwelkom en met u in aangesig kon gesels oor die nuutste inligting. Maar ongelukkig is COVID nog steeds met ons en het ons vanjaar weer 'n virtuele inligtingsdag. Die jaar 2020, 2021 en ons glo vir die volgende klompie jaar wat voorlê, gaan landbou en spesifiek landbou in die Weskaap met groot uitdagings gemoei wees. As ons kyk na die Weskaapse landbou insidentekaart, ons kan dit ook die rampkaart noem, sal jy sien dat in 2011 tot 2021 die prentjie dramaties verander het. Waar ons in 2011 2 blokkies gemerk het, het ons in 2021 al die blokkies gemerk. Ek wil u egter verseker van die ondersteuning van die Weskaapse Departement van Landbou. Ons is daar om u geleenthede beter te maak, groter te maak en ook die potensiaal van elke distrik van die Weskaap uit te bou. Navorsing en tegnologie, ontwikkeling en ook tegnologie oordrag is vir ons uiters belangrik. En daarom sal ons voortgaan ten spyte van die pandemie om hierdie inligting deur die plaashek tot by u te dra. Ons wil vandag vir u die bevestiging gee dat ons daar is met ons navorsingspoging. Ons sterkte lê egter in vennootskappe met u as boer en ook insetverskaffer. Dankie dat ons weet dat u ons vennoot is. Rampe gaan 'n uitdaging bly. Klimaatsverandering is hier om te bly. Maar as ons saamwerk, kan ons die landbousektor meer weerstandbiedend maak, meer klimaatslim boer en ook seker maak dat ons die beste produksie het met ons beskikbare hulpbronne. Ons navorsingsspan is toegewyd, hulle is gefokus op u probleme en ons navorsingsportefeulje groei. Dit sluit ook nuwe tegnologieë in en ons jongste tegnologie is dan ook ons hommeltuigtegnologie as deel van die 4de industriële revolusie. Boere maak planne. Ons het gesien die afgelope 2 jaar hoe boere regtig alles gedoen het om voort te gaan om te produseer en die kosmandjie van die Weskaap vol te hou. Daarvoor sê ons vir u baie dankie. Geniet hierdie inligtingsdag saam met ons. Gesels met ons navorsers, al is dit slegs virtueel, per telefoon of per e-pos. Ons bly u vernoot. Baie dankie en geniet die dag.
Good morning, everybody. Today I'm going to be talking to you about climate change and opportunities for dairy farming. So today I'm here at Outeniqua Research Farm in the Southern Cape. But during my talk, I will also refer to some of the other dairy farming regions in the Western Cape, so up the West Coast and in the southwestern region, the Western Overberg. And it's important to recognize that these 3 regions have very different climates. And some of the maps that I'm showing you will illustrate that we have gradients of temperature, of rainfall, and of rainfall seasonality. And so we have very varying conditions for dairy farming. And we need to take this into account when we look at what the future might hold with climate change. So first of all, I think it's important to note that climate change can impact dairy farming along 3 main pathways. The first is obviously the direct impacts on the animals around heat stress and other issues, health and so on. Then of course the pastures respond to the climate changing. They respond to warming, to rising carbon dioxide levels, to different rainfall patterns. And so the productivity of the pastures is likely to change. And of course, then the last one is the impact of disasters. And I think we've seen around the world now how climate change is increasing the frequency and impact of disasters, droughts. We've had our own drought recently, and flooding and other disasters. So those are the 3 types of impacts, and of course the driving forces behind all of this is the greenhouse gas emissions. And so in this presentation I'm going to present a little bit around the actual greenhouse gases and how dairy farmers can make a contribution to dealing with that issue, but then also some of the issues around pastures and opportunities around pastures. So I'm going to focus on two areas basically, and the one is natural resource management, and I'm going to refer specifically to water management. And you'll see the sprinklers in the background. Many pastures are irrigated and use quite a lot of water, so that will be one part of my talk. And the other part will be looking at how we can, with smart farming practices, make a contribution to reducing the greenhouse gas emissions from dairy farming. So the first few slides I'm going to just show you what is happening in terms of climate change globally, very briefly, and then also what is happening in the Western Cape, quite specifically, and then what the future is likely to hold. So the climate modelling that shows that in this part of the world we are going to see continued warming. We're likely to see more warming up the west coast, so that might be an issue in terms of heat stress for cows, but everywhere we are getting extremes and more variability of temperatures, of rainfall. And what's really concerning is that the latest science shows that all across the province and many other parts of South Africa, the prognosis is not good for total rainfall. So we're likely to see a drying future with more droughts, more agricultural drought, and a growing gap between water resource availability and the demand for water, and also evaporation of water from farmlands.
Good day, everybody. Today I'm going to give a presentation on climate smart dairy farming, opportunities for carbon mitigation and improved resource management. I'm Stephanie Midgley. I am a climate change scientist with the Department of Agriculture in the Western Cape. So as an introduction, we know that the agricultural sector of South Africa, the Western Cape, is already experiencing impacts of human-driven climate change. There's a real urgency now to intervene to limit the extent and impact of future climate changes by rapidly reducing both the sources and enhancing the sinks of greenhouse gases. Pasture-based dairy production offers several opportunities for cost-effective reductions in emissions of key greenhouse gases and for meaningful and even profitable carbon sequestration interventions. Simultaneously, climate change is also placing great pressure on our scarce water resources, and these must be better protected and managed. This paper focuses on the farm level, the emphasis on pasture management, and it aims to provide an overview of, firstly, climate change trends and projections in the Western Cape, opportunities to reduce greenhouse gas emissions, opportunities to sequester carbon in pasture soils, and finally, protection and efficient use of water resources. I'm going to focus on the three main production regions in the Western Cape, namely the Western region, the Overberg, and the Southern Cape. And this is a map showing the smart agroclimatic zones that we're using in the Western Cape Department of Agriculture for our climate change program. It's important to note that these three regions have widely differing climates in some respects. So first of all, if we look at the top left map, this is a map of mean annual rainfall. We can see that the West Coast and the Overberg have relatively low rainfall through the year, whereas the Southern Cape is a much higher rainfall region on average. Then if we look at rainfall seasonality, which is the top right graph or map, and we see that there's a shift or a transition from core winter rainfall in the western side, which is the light blue. Along the Southern Cape coast, this shifts towards all year rainfall, which is in the dark blue. And you'll notice that the Overberg region has that transition within the dairy farming region from winter rainfall to all year rainfall. And then if we look at the bottom graph, that is mean annual temperature. And here we see that there's not that much difference in mean annual temperature between the three regions. But on maps, which I'm not showing here now, we can see that the summer temperatures and hot days are much higher in the Western region than in the Overberg and the Southern Cape region. So this means that we have a very diverse range of production conditions for dairy farming, and it's important that we need to look at the local context, the local climate, especially when we start thinking about interventions. That is a very important consideration. And then also when we start to overlay the climate change projections, we get a matrix of different conditions. So if we look at what's already been happening in the Western Cape in terms of climate shifts over the last 100 years or so, climate is changing at the moment through increasingly variable and unpredictable weather. Certainly significant rates of warming are measured, and also more frequent climate-related extremes and disasters. And some of the pictures in the bottom show some of the recent disasters that we've had. The temperature rise has been greater than average globally. It's been more than 1.1 degrees Celsius on average, in some places much higher. You're getting more hot days, and the hot days are getting hotter. We're also seeing increased heavy rainfall, but fewer rain days in the late summer and autumn, and then more rain days in November and December, especially in the western parts, where the early summer season seems to be getting a little bit cooler and wetter. We're seeing very few trends in annual rainfall, except for a small positive trend in the Little Karoo in the summer. Now, if we look at the futures, and this is the climate modeling that is done using different, it's an average of different climate models. If we first look at the rainfall-related modeling, we see that reductions in winter rainfall are, for most models, agree that there will be a reduction in winter rainfall, especially in the western side of the region, the western winter rainfall region. And you can see the red there indicates the much higher reduction in annual rainfall. Then we're also expecting more frequent and longer dry spells and droughts, and I'll come to a map showing that, and also frequent and intense rainfall events and floods. So things just getting rather unstable and erratic and difficult to manage for farmers. So the idea is that these trends will emerge by the mid-century, and in the short term we will just see this as increasing variability of rainfall in the next 2 or 3 decades, and then from mid-century onwards, probability that it'll just be getting drier across the whole region. Then if we look at this map, comes from the very recent IPCC report, the Intergovernmental Panel on Climate Change, that's just released its 6th assessment report. And this is a very important study to look at very carefully what they're saying about our region. And what they're saying is that we're expecting in the Mediterranean regions, particularly, this decrease in winter rainfall and an increase in future drought risk. So what they're saying is quite well agreed amongst all the studies that have been done, is that in our region we are expecting, for example, with the 2 degrees warming, which is probably a minimum of what we're going to reach, we're increasing aridity, more agricultural and ecological droughts. Also increases in mean wind speed, and also increases in fire weather conditions. So the science really is showing that we are heading for quite a difficult future, possibly.
When we consider our water resources, and that's closely linked also with the way we manage soils, so pasture management basically, and irrigation management, there are a couple of things we need to consider. So we are going into a future with scarcer water resources, which means that we need to make sure that we have enough supply, it's reliable, that we have a diverse range of water sources. Many people are using groundwater already, but using that sustainably. And then, of course, making sure that we are not polluting those water sources. And dairy farming also does play a role in trying to reduce water pollution from manure management, for example. And then the other thing is we need to look after what we call our ecological infrastructure. So what that really means is that we need to look after our river courses, clearing away the aliens that are sucking up the water, making sure that we conserve our wetlands, and we use nature to regulate our hydrological flows. And that means that more water becomes available in the system to farming. So water efficiency is another one that we really need to look at carefully, and we can increase our water use efficiency even more through using the correct irrigation systems and scheduling. We use precision tools, for example, Fruit Look, to make sure that we are as efficient as we possibly can be with our water resources, and we don't have any runoff that is excessive. And then if we come to pasture management, There are, of course, many opportunities for using conservation agriculture, which basically means looking at our crop species composition, rotations, including more perennial grasses, for example, making sure that our soil structure, our soil health is improved, and that, of course, also increases water holding capacity in the soil.
Now, if we look at temperature-related projections, this map shows the change in temperature that is expected across the province, and the blue shows the slightly lower rate of warming. Along the coast, we're expecting roughly between 1.5 and about 2.1 degrees Celsius warming, and that you can see covers the Overberg and the Southern Cape region. Whereas on the west coast, the yellows and oranges are slightly more, 2.2 to about 3 degrees Celsius. The reds go even above that in the interior. So we're seeing what the projections are saying is more hot days and warm nights and fewer cold days and nights. Of course, this leads to an increase in evapotranspiration, which then results in a greater water demand by plants, by pastures. And then, of course, increasingly favorable fire conditions, especially where wind speeds are possibly going to pick up. Now, if we combine all of this and we look at the three dairy regions, I'm not going to go through it in detail, but what really comes out is that the western region is already warmer in summer. There's stronger warming in the future projected, more very hot days. We're certainly expecting a winter rainfall drying in that area, increases in aridity and droughts and so on. In the Overberg, it's a slightly moderate warming, the same in the Southern Cape, but also more hot days. In the Overberg, also because the western part is more winter rainfall, those areas expected to possibly dry more than the eastern parts, where we're not quite certain what the shifts are going to look like, the annual and the seasonal shifts. The models are not really in good agreement there. And then the same for the Southern Cape as well. And in the Southern Cape, there are even some models that show possible wetting in the short term in the western part, so around about the Mossel Bay area. But we'll have to see. We aren't terribly certain about these projections for rainfall, and we need to keep monitoring. All right, and in the Southern Cape, unfortunately, we're going into the eastern part of the country, where the projections are also for more increased heavy rainfall and flash flooding, and that could be of concern to those production regions. The impacts on dairy production systems really occur through three pathways, and I'm not going to go through the details of these, but really the three things we should be looking at is the impacts on pasture productivity and quality, and that of course is directly impacted by changes in rainfall, temperature, carbon dioxide and so on. Then we see direct impacts on animal growth and health, and especially through heat intensity and nutrition stress, pests and diseases. And then we see the impacts of extreme weather events. And here we're talking about heavy rainfall, floods, extreme heat, droughts, extreme cold, and so on. I'm going to focus in this presentation mainly on the impacts on pastures, and I'm just going to refer a little bit also to the extreme weather events and the animals. So first, let's go back a step and let's see where dairy farming fits into the South African picture in terms of greenhouse gas emissions. We need to be careful about approaching this in a scientific manner. What does the data say? And of course, all these inventories and accounting systems are not perfect, and so we need to keep on working at them to make sure we get the right results. But we do see that the latest national inventory for greenhouse gases shows in rank number 7 and rank number 8 in terms of emissions. We see enteric fermentation by cattle accounts for about 3.8% of our total greenhouse gas or carbon dioxide equivalent emissions, and direct nitrous oxide emissions from managed soils, in other words fertilized soils and irrigated soils, is at about 3.15%. So in total, we're seeing a contribution of about 9% if we look at all the greenhouse gas emissions. So this isn't insubstantial, it is rather significant, and we do need to look carefully at how we can address this, because South Africa is the 15th largest emitter of greenhouse gases per capita in the world. So we do have a shared responsibility to intervene in ways that protects our industries and food security, but also starts to bring these numbers down. If we look at the bottom right-hand picture here, this comes from the National Greenhouse Gas Emissions Report of 2020. The bottom right-hand graph is all greenhouse gases expressed as a CO2 equivalent, and it's always the yellows in these graphs that represent agriculture. what they call a FOLU without the FOLU. With FOLU is forestry and other land uses, but in this case we're showing only the agriculture part. So the yellow shows that agriculture contributes about 9%. It's been a fairly constant proportion over the years, the last 10 years, which is good, but we would like to also start bringing that down. Then if we look at carbon dioxide as the top left graph, we can see that really agriculture hardly features there in comparison with the energy sector, so electricity, and also the blue, which is the industry. And carbon dioxide thus from agriculture mainly relates to changes in land use, and that hasn't really happened a lot over the last few years. So where we need to really focus is methane, which is top right, and nitrous oxide, the bottom left. And you see the yellows there are quite dominant. In terms of methane, we can see that the methane proportion coming from cattle has decreased slightly over the years. The waste sector is increasing, that's the dark green. And we see that of the methane, being emitted by cattle, dairy cattle accounts for about 12% of that, of enteric fermentation. If we look at nitrous oxide, this is mainly from nitrogen fertilization and manure. There's been a slight decrease because of the cattle numbers decreasing, but if we look at the dairy proportion of that, it's been fairly constant. In fact, there's been a slight uptick. And so nitrous oxide, you can see, is an area in agriculture that really must be looked at in more detail. Now, if we look at opportunities to reduce greenhouse gas emissions in pasture-based dairy farming, so the main one to really look out for is nitrous oxide emissions resulting from synthetic nitrogen fertilizers and to a lesser extent from animal manure. So the objective really should be to raise and to optimize what we call nitrogen use efficiency. That is the nitrogen that is not exported. In other words, it's used efficiently for production purposes. It's not lost in the system. And we really can do this through more effective and affordable fertilization and feeding strategies. So the idea really is to start reducing and minimizing synthetic nitrogen fertilizer application rates. And then in conjunction with this list that I've listed here, so there is a role also for concentrates to become more, or to use feeds that are more efficient at or feed conversion. Then trying to optimize milk production per hectare in terms of nitrogen use efficiency, and there's some good studies on that came out recently. Optimizing for nitrogen use efficiency using stocking rates, and all of these can be done without forfeiting production, milk production and value. And there's been some good studies to show how this can actually happen. Rotational grazing management is another one. Then considering the contribution of manure and urine to the N balance and the fertilization strategy, the optimal timing of fertilizer application to make sure that there isn't excess application at certain times and therefore higher emissions. Incorporation of forage nitrogen fixing legumes, improved irrigation systems, and then also increasing soil carbon levels. And these are all things that have been shown to be effective in reducing nitrous oxide emissions. If we turn our focus now on carbon and the opportunities to fix carbon, to basically use plants and photosynthesis to capture carbon from the atmosphere and to make sure that it gets incorporated into the soils. There are a few things that we can look at here. For example, applying the principles of conservation agriculture in managed pastures through minimal soil disturbance, preferably no-till, keeping the soil surface covered, and using forage rotations and a greater diversity of forage species, including legumes. Then including perennial grasses and other perennial forage species, because these have deeper root systems, long-lived root systems, that increases the below-ground biomass fraction and the carbon that is fixed and kept at lower soil levels. And then also optimizing forage growth and biomass per hectare, but without using excessive fertilizer and irrigation. And then multi-paddock rotational grazing and high stocking densities. And these have been found in many instances to be effective. Carbon offset programs have become feature in the landscape. Agriculture and farmers are becoming really interested in what these have to offer. So the idea is that there are direct financial benefits available to farmers in terms of carbon credit revenue. The aim is to promote long-term carbon fixation from the atmosphere and accumulation in farm soils. And one needs to be just a little bit cautious. I think it's a wonderful opportunity for farmers, and there are some good programs now available in South Africa, but one needs to just be careful that these interventions have to be additional to existing practices. It's not based on business as usual. It needs to be, you need to be able to prove that it's a new practice. You must be able to provide existing soil data over several years. The additionally fixed carbon must be persistent. In other words, it must stay there over the long term, and we're talking here about many decades, 100 years and more, in a stable form, because it doesn't help to fix carbon that is then lost again over the next few years. And then using only programs listed under an internationally recognized carbon standard. Lastly, I want to talk a little bit about water resources. In dairy farms, do you use water? In some instances, permanent irrigation systems that are running with using quite high volumes of water. We are living in a very water-stressed part of the world. There's increasing variability of rainfall and water resources, and with the warming, we're seeing an increasing water demand from plants and increasing evaporation. So the gap between water supply and water demand is going to grow. Groundwater has been used increasingly, especially during the last big drought, but we need to be really careful of protecting that resource as well. Deteriorating water quality is a major risk, and it's possible that this could worsen. We need to keep an eye on that. And then dairy farming regions do not benefit from very large water storage capacity, for example, the big 6 dams in the Western Cape. The dairy farming regions generally rely on smaller farm dams, on rivers, and we know that engineered water structure is reaching its limits, so just always building new dams is also not the solution. We have to become more efficient in our agricultural water use to make sure that we maintain productivity but using less water. Improving our catchment management, clearing our river courses and wetlands of invasive alien plants, and really looking after our ecological infrastructure, which is basically saying using nature to do what nature does best, and that is hydrological flow management, and to make sure that even in dry seasons that rivers and the wetlands are still providing that base flow. And then we need to look at, are we prepared for more frequent and intense flash flooding? Do we have fit for purpose drainage infrastructure? And ecological infrastructure, once again, can be used very cost effectively here to make sure that our drainage works under high rainfall. I've got a long list here of what can be done on farm to protect water resources and use them more efficiently. These are points that I think everybody could go through in their own time. Some of them relate to just reducing water volumes, making sure that we use systems that are more efficient, for example, drip systems, using the irrigation guidelines that are available for pastures correctly, using drought-resilient species in the pasture mix, species with deeper root systems, for example, measuring and using tools such as Fruitlook to guide irrigation scheduling to be more precise, expressing our water use in a way that puts the value on water and not just on hectares. So instead of just expressing it as liters of milk per hectare, making sure that we know what our liters of milk per liter of water used is, for example. We will call that water productivity. So the value of our product, of the milk or whatever it is, of the cheese, in terms of the water that is used to produce that product. Increasing soil water holding capacity, then making sure we don't lose water through leaks in our systems or through pollution. Sometimes there's an opportunity to increase on-farm storage capacity. Sometimes there's an opportunity to use other sources of water. Recycling and reusing wastewater is a very important one, I think, in dairy operations. And then making sure our water courses are cleared of aliens so that we get those rivers flowing again. Making sure the buffer zones are maintained between managed pastures and those water courses and wetlands. And making sure that drainage infrastructure is well designed. All right, and in conclusion then, just a couple of thoughts here. So one might ask, what about the cost? Definitely we need economists, people to run the numbers. The cost effectiveness of specific interventions is highly region and farm specific, and it requires doing those sums on a case-by-case basis. But many of these interventions or these opportunities are linked to reductions in inputs, costly inputs, and that already means that it is affordable, and in some cases there is an investment that requires a return on income, but generally there are opportunities that do not cost a lot of money up front. The dairy sector needs to ensure its resilience and its growth, and I think in the current environment where there's a lot of pressure on livestock farming in the climate change picture, we really need to proactively shift while we have this window of opportunity, which is probably about 5 to 10 years, to really show, using measurement, using analysis, that the sector is able to reach those environmental and climate benefits and continue to provide healthy food to the population. Then future research, I think there's an opportunity to look at long-term shifts in pasture production potential. Some of this relates to the warming that's happening, some of it relates to the rainfall changes, to the atmospheric carbon dioxide concentrations that almost act like an additional fertilizer for plant growth. We need to look at changes in the length of the growing season for pastures in the different growing regions. We need to look at the rising water demand of pastures. What is our water balance in various areas? And then how does soil warming affect biological activity in various soils and greenhouse gas emissions? And then, of course, the impacts of more severe droughts and floods and how to become more resilient to those. So that's the end. Thank you very much for your attention. And if anybody would like to contact me, here are my details. You can email me at stephaniem@elsenburg.com or give me a ring. I'd love to hear from you. Thanks very much.
So these are the trials which form the basis of all the data that we present in our annual information day and which we otherwise also share with farmers. And I just want to explain sort of a little bit of how we do these trials, why we do them, and what their function is. So a lot of pasture species and varieties that are used in South Africa in mainly dairy, but to some extent also beef and sheep production, are imported from other parts of the world. So they originate either in Europe or New Zealand, some in South America. They are also bred in those countries, meaning they are bred in those climates. Then they are brought to South Africa to be sold here, and we need some sort of system of working out what is actually adapted to our specific environment, to our climate, and how we use pastures in our pasture systems. So for different species, we have different trials. This, for instance, is a tall fescue trial, which will run over a 5-year period. We have Italian ryegrass trials, which run over a 2-year period, and then we have perennial ryegrasses, for instance, which will run over a 3-year period, and so on. We also evaluate things like forage cereals and chicory and plantain to be able to collect data on how these different varieties are adapted to our climate. The way we do it is we look at the genetic potential of each variety. And what that means is that the trials are designed in a statistical way. So there's a certain statistical design, and each variety is repeated 3 times throughout the trial. And that is a random allocation within the 3 replications. And then everything is kept the same. So they all get the same water, the same fertilizer. They're obviously exposed to the same temperature. They're cut in the same way. Everything is exactly the same. And then the differences we see are basically based on the genetics of each variety. So the plant's genetic potential will then show up, and that we determine by providing optimal conditions so that we can determine what is the maximum potential of each variety in our specific climate. So if we look at the different trials that we do, we run standard trials and we run elite trials. The standard trials we use to evaluate the cheaper varieties or older varieties, and the main focus is yield and rust resistance. So those would be for sort of lower input paddocks, but we would still like to provide farmers with information of what to use in that sort of situation. And the reason we look at rust is because rust races change over time. So if a variety is already relatively old, it might over time become susceptible to rust, and that would be an important factor to know. And then yield is always important. Most of the trials that we run are elite trials, and there we look at a lot of different parameters. Obviously, first and foremost again is yield, because that drives the productivity of the whole system. But we also obviously again look at rust, and then we look at flowering, for instance. When does the specific variety flower? For how long does it flower? And the reason we look at flowering is because that will have an influence on yield and on forage quality. So yield, we don't only look at the total yield, say over a year, we also look at the different yield distributions over seasons. So is it good in winter, or is it very good in summer, or is it good in the second autumn? And often that is also related to flowering, because when the plant goes from vegetative growth to reproductive growth, it changes to a more bulky, upright a morphology where there's stemmy material, so there's more material, but it would also be higher in fiber and less quality. So it would be that trade-off. But what we look at is, does a specific variety have a short flowering window where most of the plants flower within a very short period of time, or most of the tillers, which would then create a lot of bulk in at a specific time period? Or is it a variety that flowers over an extended flowering window where some of the tillers are flowering and a whole lot are not flowering, so there would be some increase in bulk, but the forage quality would not be affected that much? And these would be used also in different contexts. So say, for instance, you have a mixed pasture and you're combining something like chicory and plantain with the grass, you might want to actually have a grass that it goes reproductive in summer to be able to compete height-wise with the chicory and plantain. If you have a mono-specific stand where you just grow one thing and your focus is mainly on forage quality, providing high-quality pasture, you would probably choose one that has a low flowering incidence over a long period of time during the spring and summer months. And there'll be other considerations as well. So basically, would you use it for silage at some stage or not? So we collect all this data to assist in the choice of variety. And lastly, we also look at the persistence of these varieties. So do they, for instance, if it's an annual, does it go into the second autumn? If it's perennial, ryegrass, for instance, how does it cope with the second year? How does it survive after the first summer when there's been a lot of heat? How many plants survive? Is the production affected? Are there certain varieties that can cope with that a lot better than others? So we provide a whole lot of parameters which farmers can then look at and make specific choices of varieties that first and foremost produce a lot of yield or biomass, and secondly have all these other characteristics that might fit specific paddocks or specific situations or specific grazing systems. So that is the type of information that comes out of these trials, and it is also important that it is independent information. So all the seed companies get an opportunity to put their varieties into these trials, but we evaluate it on an independent basis. So we would ask them to give us a certain number of varieties from each company, and it will be evaluated in these trials and then provide independent data to farmers. And that data is then mostly presented at the information day. Welcome to my presentation on an overview of ryegrass and tall fescue data for the 2020 evaluation trials planted at the Outeniqua Research Farm in March 2020.
My name is Sigrun Amon from the Western Cape Department of Agriculture. The trials were planted in March 2020, and this is an overview of the first 15 months of data. The 3 trials that I will give an overview for are the perennial ryegrass trial, which consisted of 16 cultivars, the Italian ryegrass and hybrid ryegrass trial with 20 cultivars, and the tall fescue trial with also 20 cultivars. The detailed data and information on all the parameters and any additional information is given in the booklet. And this is merely an overview of some of the yield data up to May 2021. And all these trials are still in progress. Firstly, we will look at the perennial ryegrass data. This is the yield for the first 15 months. And there were 6 cultivars that are statistically the highest yielding, ranging from 16 to 17.8 tons dry matter per hectare over the 15-month period. And they were Viscount, Governor, Platform, Legion, 50/50, and Base. Looking more specifically at what yield is possible in the first year and then the second autumn, which is shown in this graph, the best cultivars produce between 13.5 and 14.5 tons in the first year, and then have the ability to add another 3 to 3.4 tons in the second autumn. As conditions become cooler again, there is a higher growth rate. The higher yielding cultivars are also the ones that have the best second autumn yield. Let's focus on 2 of the most important seasons, being winter and summer. This is the data for winter 2020. 4 cultivars, namely Platform, Legion, 50/50, and Base, yielded better than the control, which was Nui. And some cultivars are rather winter dormant, as we can see towards the right-hand side of the graph. And it is quite a range in yield. If winter is an important season for your fodder flow, then the choice of cultivar really matters, as we can see from this graph. The other important season is summer, of course, when temperatures are quite high, which is generally less favorable for ryegrass. Here the standout cultivar was Viscount, and then there were 3 others, Governor, Base, and 50/50, that were similar in yield statistically. If we look to see if there are cultivars that do well both in winter and in summer, we see that Base features in both those seasons. Looking more specifically at the Italian and hybrid ryegrasses, which was the second trial, also for the 15-month period, we see that the Italian and hybrid cultivars had a very similar yield to the perennial ryegrass cultivars overall, in terms of the best cultivars yielding between 16.5 and 17.9 tons dry matter per hectare for this 15-month period. 3 cultivars were statistically superior, but quite a few following closely behind, and about 2/3 of the cultivars having a reasonably good total yield. Looking more specifically at the first year and then the second autumn that follows, we see that the yields for the first year are very similar to the perennial ryegrass cultivars, with the best ones between 13.2 and 14.2 tons. The second autumn then adds another 3 to 3.7 tons, depending on the cultivar. And in fact, many of the cultivars do well again in the second autumn when conditions become cooler. On the far right of the graph, we can also clearly see the difference between short and longer duration Italian ryegrass cultivars, with the last 2, Supreme Q and AgriBoost, being typical of shorter duration Italians that end after they have flowered in spring, while most of the others produce new vegetative tillers to carry on into the summer and the next autumn. And the degree to which the plants are able to produce these new vegetative tillers after they have flowered then adds to the yield and to the persistence of the cultivar. Looking more specifically at particular seasons, for winter, for the Italian ryegrasses, we see that many of the cultivars actually do well, about 2/3 of them, although the best yielding ones are still slightly lower than the best yielding perennial ryegrass cultivars in winter. This is almost surprising, but it is similar to what we have observed also for 2018 and 2019. The other important season is, of course, summer, and this is a graph for summer 2020. The summer yields show substantial differences between cultivars. The first 5 cultivars were statistically superior to the rest, with Fox, Bellucci, Shogun, and Bond also amongst the top winter performers, while Yolandi, which is the 4th cultivar from the left, was amongst the top performers in the second autumn. So this does show that there are cultivars that can do well in at least 2 of the crucial seasons. Now we look at the tall fescue and Festilolium trial. Tall fescue is another important species, and I think it will grow in importance as we experience more variable and warm climate, and as we seek to achieve more persistence in pastures and also combine with other species such as forage herbs, being chicory and plantain, or legumes like lucerne and others. One of the cultivars in this trial is actually a mixture, ultra soft, which turned out to be predominantly Coxford, with not much tall fescue visible in it as yet. So I will focus on the other cultivars. The top yielders for the 15-month period were 3 continental types and the 1 Mediterranean type that is in the trial. So that was Royal Q, Quantico, and Tawa, and then Tamora is the Mediterranean type. And the yield is quite substantial for the first 15 months, ranging from 18.1 to 19.1 tons dry matter per hectare. And Royal Q, Quantico, and Tower were the best continental types. For comparison purposes with the ryegrasses, we will also look at the tall fescue, looking more specifically at the first year and the second autumn that then follows. We see that the best cultivars are around 16 tons in the first year, which is more than the ryegrasses. And this additional yield comes mainly from the summer months. The second autumn yield is very similar to the ryegrasses, with between 3 to 3.7 tons dry matter per hectare. This graph gives the seasonal split for the tall fescue over the 5 seasons. And this clearly shows the spring and summer, being the green and the purple, being the major growth seasons for tall fescue, where for ryegrass summer is the most challenging season. For tall fescue, winter can be challenging, and in this regard, the choice of cultivar becomes really important in terms of tall fescue. This graph gives the seasonal comparison of the 3 species. And starting from the left, in the first autumn, which is the establishment season, they are all quite similar. The blue is the tall fescue, the red is the perennial ryegrass, and the green is the Italian ryegrass. If we move on to winter, which is the second set of bars, the perennial ryegrass actually does best in winter of the 3 species, as we have already seen in the other graphs. Then in the middle is spring, which is good for all species, but tall fescue is the best one of the 3. And then tall fescue has a huge advantage in the summer months, where we see about double the yield compared to the other 2. And then in the second autumn, they are all fairly similar again, but with Italian ryegrass having a bit of an advantage over the other 2. Looking more closely at the winter production of tall fescue, the highest producing cultivar on the left is, as expected, the Mediterranean type, being Temora. This is, however, higher in fiber and can thus not really be used on its own in dairy pastures. The next highest group are 4 continental types, with Royal Q producing about 1.5 tons less in winter than the best Italian and about 1.1 tons less than the best perennial ryegrass in winter. Lastly, we look at the tall fescue yield for summer, which is really its most productive season, with the good continental types producing between 5 and 5.5 tons, and they are also the ones that produce well in winter. So a good combination there, and that is why I said it's important to choose the correct cultivar, because some of these are really dormant in winter and others are fairly dormant in summer. So the choice of cultivar is really important for these different seasons. So why tall fescue, we may ask, and the question arises why we should grow tall fescue if it is much easier to grow ryegrass. But there are various reasons why we should consider tall fescue. It has better persistence, which means that part of the farm could be left in the grazing rotation without the need for oversowing, while oversowing slows the rotation. So it could improve the overall fodder flow on the farm. The deep root system has a definite advantage and has a knock-on effect on quite a few of the other characteristics. And tall fescue resumes root growth immediately after grazing, whereas ryegrass first prioritizes leaf growth and then root growth. Tall fescue equally partitions carbohydrates for storage in the base and the roots and for leaf growth, whereas the ryegrasses prioritize leaves over roots and storage. Tall fescue also tolerates higher temperatures than ryegrasses, and all this means that it is very responsive to irrigation and rainfall and has a better water use efficiency than ryegrass. It does have a different seasonal production pattern, which needs to be taken into account, but most likely it can be managed as part of a system that also has other species in it. So I think there is good reason for considering tall fescue for at least part of the pastures on any particular farm. And that brings us to the end of this overview of the yield data. And more details are available in the booklet, and you're also welcome to send me an email if you have any specific questions. Our email addresses are given in the booklet. And I would just like to thank the Plant Sciences technical team and also Farm Services for playing a major role in keeping all these trials going and harvesting them, and the data collection that happens basically weekly on all the different trials. Thank you. Welcome to my talk on changes in herbage yield and botanical composition in forage herb grass binary mixtures over a 4-year period. Basically, we had a trial of pure stands versus binary mixtures, and the objective was to the use of alternative species as intensive pastures other than ryegrass. So what we had in the trial was perennial ryegrass, cultivar Arrow, Coxford, cultivar Adrema, tall fescue, cultivar Optima, which was a continental type, summer active and winter dormant. Then chicory, choice, which is a large leaf type, and plantain, the cultivar Tonic, which is summer and winter active. And the questions were how best to use these forage herbs and grass species to improve yield, both the annual yield and the seasonal yield. The trial was established on Outeniqua Research Farm in the Southern Cape on 5 October 2015. The harvesting cycle was determined by perennial ryegrass at the 3-leaf stage, and the data we collected was dry matter yield, botanical composition, and forage quality. The treatment combinations in the pure stands, we had perennial ryegrass, cocksfoot, tall fescue, forage chicory, and narrow-leaf plantain. And the binary mixtures consisted of chicory cocksfoot, chicory tall fescue, chicory perennial ryegrass, and then plantain with those 3 grasses. And we also had a chicory plantain mixture, which are represented by these abbreviations. Some of the key questions that we tried to find answers to with this trial were: how does botanical composition change over time? How does the annual and seasonal yield change over the years? How does the composition influence the yield? And can mixtures address the autumn gap and still be competitive in winter? Can we maximize yield using either mixtures or pure stands, or comparing those two? Which one is better at maximizing yield? And what are the advantages and constraints of mixtures versus pure stands? Looking at the results, this is a graph showing the chicory cocksfoot yield and composition. The yield is shown by the bars, the light blue being chicory, the orange being cocksfoot, and the lines represent the percentage composition on the right-hand axis of the graph. And the dotted line represents the yield trend over the 4 years. And basically what we see in terms of yield is that there is a decline over the 4 years, and the slope of the graph is minus 1.3. So we did have a slight increase in year 3, and that was mainly related to the cocksfoot. In terms of composition, if we focus on the 2 lines, the dark line being the chicory, that declined steadily over time, and at the same time the cocksfoot increased in composition. So after 2.5 years, there was the inflection point of the 50-50, and after that the cocksfoot became dominant and the chicory became decreased in composition, and we ended up with the 70-30 in year 4. And the yield component also changed, with initially the chicory dominating and later the cocksfoot being the major contributor to the yield. For chicory tall fescue, we found that again the yield decreases over time at a slightly greater slope of minus 2.1. Again, we see that the chicory initially dominates, the dark line, and then it decreases. The tall fescue starts very low, and then it increases in composition, and the 50-50 is reached in year 3, and in year 4 it also goes to 70-30, 70 grass, 30 chicory. For the perennial ryegrass, the picture was somewhat different in that the perennial ryegrass yield contribution in terms of the orange part of the bar graph was relatively small, and the yield reduction of the total of the chicory and the perennial ryegrass also had a very deep decline, as shown by the dotted orange line. and as you can see by the bar graphs, and the composition was also different in that basically the grass never dominated. So the perennial ryegrass remained the minor component of the pasture. And if we look at plant population, which is represented by the blue dotted line at the top of the graph, we see that there is a decline after year 2. And this is different to the other grass chicory mixtures. So yes, we do see in the other mixtures as well that the chicory declines after the second year, plants are being lost. But in this case, the perennial ryegrass also declines in population after the second summer, as we so often see with perennial ryegrass, which means that the sward was opening up and was at around 50% at the end of year 4, whereas the other combinations, the sward density remained at 100% by the grass component taking up the gaps where the chicory plants had been lost. Getting to plantain, plantain cocksfoot. Plantain yield is represented by the dark blue in the bars and the cocksfoot the orange. Here we see that plantain was the major component of yield in the first 2 years and later on contributing also still a large part of the yield, about 50%. And then the composition represented by the lines, again the solid lines. Initially the grass, being the cocksfoot, is very low, 10% for the first 2 years, but then it increases to about 50%, and the plantain decreases to about 50%, and it seems to stabilize at a 50-50. The dotted blue line again represents the yield decrease. So there is a yield decrease also over the 4 years. But what is important to note with the chicory grass mixtures, the highest yield was around 20 tons, whereas here we are at about 26 tons and then decreasing to about 16. So even though the decrease is similar, minus 3.3 slope on this line, the end point is still reasonable considering that it started higher. If we look at plantain tall fescue in this graph, here the plantain really, the dark blue bars, it contributed most of the yield. And the tall fescue only really started to contribute to the yield in year 3 and 4. So looking at the composition, the red line being the tall fescue, it was almost non-existent in the first 2 years in the sward, but then did increase. So the plants were still there, and it got to approximately approaching a 50-50. And the plantain was extremely dominant and then started reducing and also moving towards that 50% mark. Again, the yield starts about 26 tons dry matter for the first year and has a decline, slightly higher decline than with the cocksfoot, mainly because the cocksfoot contributed a bit more to the yield in the latter part of the trial than the tall fescue, and but again it ends, the end point is below 15 tons in this particular combination. Again, we see for plantain perennial ryegrass that the perennial ryegrass hardly made an impact in that mixture, and here really the main yield component is simply the plantain. And again, there's a yield reduction over the 4 years, similar to what we see in the other combinations. And it is basically driven by, the yield is driven mainly by the plantain. the perennial ryegrass contribution is very minor in this, in terms of annual yield. So it really did not compete with the plantain. Looking at seasonal yield of the pure swards, the chicory is represented by the blue dotted line and the plantain the red dotted line, and the grasses are the solid lines. We can again see this decreasing trend over years. The blue in the background represents the autumn and winter period, and clearly we see that most of the yield is in summer and the lower yield in autumn and winter. We do see though that the plantain is the highest yielding species in this graph, followed by cocksfoot and the chicory initially in the first 2 years. The tall fescue had very low yields in the winter months. The perennial ryegrass slightly higher, the chicory also very low in winter as we would expect. The tall fescue, that was also probably a function of the variety, which is a very winter dormant variety. So that could maybe look slightly different if it was a different variety or cultivar. But ultimately what the pure stand tells us is that the plantain was really the outstanding yielder, followed by the cocksfoot. If we look at the seasonal yield of the mixtures, the chicory mixtures are represented by the dotted lines, and the plantain mixtures with the grass by the solid lines. And then the chicory plantain is the black line, which lies pretty much in the middle. And we basically see the advantage of the plantain in the plantain grass mixtures. Again, we do see here in the summer of 2019-20 that the chicory mix with the cocksfoot was quite superior, and also towards the end, but that was mainly driven by the cocksfoot yield rather than the chicory yield. Finally, the total dry matter yield over the 53 months that the trial was running shows that the highest yield, approximately 91 tons dry matter per hectare, was achieved by the pure stand plantain, followed by the plantain cocksfoot combination. In this graph, the plantain perennial ryegrass combination has quite a high yield, but from the previous composition data graphs, we know that that sward was really dominated by plantain and had very little perennial ryegrass in it. And similarly, the plantain tall fescue, that yield is mainly plantain. So from this graph we can see that a pure stand plantain is also extremely competitive and definitely an option, as is its combination with something like cocksfoot as a grass component. All the chicory combinations were lower yielding than the plantain. Discussions and conclusions. So the highest yield was really attained by the plantain pure sward and the plantain cocksfoot. Looking at botanical composition, chicory cocksfoot, chicory fescue. The chicory starts as dominant and it moves towards a 50-50 after about 2.5 years, and then a 70-30 with the grass component dominant, and still 100% population cover where the grass takes the place of the chicory plants. The chicory perennial ryegrass, the chicory remains dominant, the perennial ryegrass remains a minor component throughout, and there is a population decline. Regarding the plantain cocksfoot and plantain tall fescue, the plantain starts as very dominant, over 90% in year 1 and 2, moves to about a 55-45 later, and that is where it settles, so also almost a 50-50. And the plantain perennial ryegrass, again, the plantain is dominant throughout, and the perennial ryegrass is unable to compete. If we look specifically at what we have learned from this trial, firstly, the forage herb component. The chicory decreases from the 3rd year onwards, while the plantain is a lot more persistent than the chicory. And for both chicory and plantain, we must use winter active cultivars. And we know that there are big differences between the cultivars in this regard, so it is important to choose a winter active cultivar. And we also know that spring planting favors the forage herbs. Looking at the grass component, the cocksfoot and the tall fescue start as minor components, but over time they increase to approximately a 50-50 composition if it is plantain, and to a 70-30 for chicory in the 4th year. The perennial ryegrass was not competitive, especially if it is not a very upright growing type or cultivar. So to choose the cultivar carefully becomes very important. It must be a cultivar that fits the mixture and that is competitive. For tall fescue, that means it must be upright growing and it must be a more winter active cultivar. For perennial ryegrass, it must also be more upright growing, and maybe it needs to be a tetraploid because those tend to be more upright growing to be competitive. However, word of caution, the low NDF could be an issue if concentrate is fed at relatively high levels. So what this trial has shown us, if we are looking at yield only, the grass component is less important, but it could be different if we analyze the forage quality, and we have done that, but we still need to look at that data. The cocksfoot and the tall fescue are expected to provide a bit more NDF, and this could be especially important at higher concentrate levels. The grass component provides diversity, and we know that that can be beneficial to the diet and the soil. The grass component improves ground cover, especially with the chicory where we have a lot of open areas in between the plants. And we need to investigate if the grass component should be added later, if that is possible from a competition point of view, if the mix is spring planted as this one was, and knowing that spring planting favors the forage herbs. You are welcome to contact me via email if you have any questions. The email and contact details are given in the booklet. And I would just like to thank the Plant Sciences technical team for all the fractioning they did for us to determine this composition data over a 4-year period, and also, of course, the harvesting and everything that goes with it. Thank you very much.
Hi everyone, my name is Janke, and today I'm standing here in one of the pastures we're evaluating in our current system trial. Now, this particular pasture was established in autumn of 2020, so just over a year ago, and we did that by spraying out the entire area and then no-till planting what I like to refer to as my complex pasture mixture which consisted of ryegrass, plantain, chicory and lucerne. And the reason I'm standing in this pasture today is to discuss some of the complex changes that occur in the botanical composition and also show you what it currently looks like. So what happened with this pasture is that after establishment in the first winter and in the early spring, the pasture consisted mainly of ryegrass, so that was our predominant component, with very little contribution made by our broadleaf components lucerne, plantain and chicory. As we moved into late spring and the summer, the chicory really started coming in and taking over with a similar pattern, but to a lesser degree with our plantain and our lucerne, and the ryegrass started going down. By the time we got to autumn, when we would typically walk into our pastures and decide what we had to do in terms of renovation, so did we want to oversow or not, we found that there was still some ryegrass left, but we really wanted to focus on the perennial herb components and the legume component. And based on that, we said, okay, well, there's enough chicory, but we want to kind of bring in a little bit more plantain and lucerne. So what we did then is we grazed it nice and short, or as short as practically possible, so that we wouldn't damage the plants and negatively affect animal production. And then we simply went in with a no-till planter and planted in the plantain and the lucerne, which brings us to where we are now. So right now in the second winter for this pasture, you can see that according to me it's quite a balanced composition. So you have a little bit of lucerne, you've got some chicory, you've got plantain, so everything is really there. And this kind of change in botanical composition over time, which according to me is quite dramatic, really highlights one of the challenges with these systems. The first big question we have is what's really driving these changes in botanical composition? So is it something that we're doing, which of course is an advantage in terms of the way we're doing these trials? Could it be that it's grazing interval or grazing intensity that's impacting the persistence of the species? Could it be something beyond our control, so climatic and edaphic factors like temperature, rainfall and soil moisture? Or is it maybe as simple as it's characteristic of the species that you're including in the system? With this in mind, we really have to start looking at how we're going to manage this change in composition, and that we will do through things like pasture establishment and renovation. So the questions we're really asking is, firstly, when do we renovate? Do we renovate or oversow these pastures every single year, every second year? And when do we completely re-establish the pastures? Or do we simply come in and we oversow it very strategically with specific species? Or do we oversow the entire perennial mixture at a lower seeding rate every year? So the bad news for our producers is that we don't have all the answers, especially in terms of how to manage botanical composition in these systems. The good news is that this keeps me in my job. So hopefully going forward we're going to be able to do some really interesting work on how to manage changes in botanical composition of complex pasture mixtures.
Hi everyone, and welcome to my presentation titled The Integration of Forage Herbs into Systems, Lessons Learned from Farmlet Studies. So before we delve into a mountain of data, I think it's important that we indicate why we need to do systems research. So component research is often very focused and answers very specific questions within a particular field. For example, in soil research, we aim to maintain ideal soil health and investigate how soil water, structure and nutrients will impact plant yield and forage quality. While in plant research, we tend to aim to have species that are high yielding and of a high forage quality, with some focus on palatability as it affects intake. And at this point, the animal research tends to take over to determine how pastures will affect milk yield and composition. However, in grazing systems, there are often other interactions that may be uncharacterized when different components are investigated in isolation. For example, the trampling and grazing actions of animals can affect the persistence and yielding ability of pastures, while plants can also affect the soil due to rooting characteristics and carbon or other cycling as material decomposes. And finally, grazing animals cycle nutrients via manure and urine, which may impact the soil, while hoof action can also impact soil structure. So system research attempts to combine all these components into one single trial to more closely mimic what happens on farm, and thereby characterize a complete agricultural system. And with this in mind, we are currently underway doing innovative system research on Outeniqua. The new systems research is innovative for two reasons. The first relates to the species we are integrating. So traditionally our pastures were grass monocultures, highly fertilized, and the species they were primarily based upon showed poor resilience to environmental stresses like drought or extreme temperatures. But thanks to groundbreaking work done on Outeniqua by my colleague Sigrun on novel pasture species like chicory and plantain, as well as species not typically integrated into pasture systems like fescue, we are now able to create and evaluate systems based on diverse pasture species and mixtures, which hold the potential to improve nutrient use efficiencies by either including legumes that can fix nitrogen or ensuring that we are yielding much higher at same application rates of nitrogen. And then finally, that can hopefully improve resilience by being more tolerant to adverse conditions or utilizing water resources more effectively due to deeper root systems. These are indeed exciting times for planted pastures, but I fear there are still many unanswered questions. For example, how will the inclusion of these alternative species and mixtures affect the yielding ability of our systems, both in terms of total pasture yield and milk yield per animal? Secondly, how will the integration of these systems affect our seasonal fodder flow, so the availability of feed throughout the year? Thirdly, will we need to make a shift in terms of our stocking rates? Here you'll have to look at how the milk yield per cow relates to the grazing capacity. Also, we need to consider the feed conversion efficiency, in other words, how effectively cows are producing milk off of what we're feeding them, and then the nutrient utilization efficiency of the pastures, as determined by the yielding ability at specific rates of nitrogen application. Also, we need to consider how especially the mixtures will change over time in terms of botanical composition. So how much will weeds contribute to our pasture yield, and also how will the composition in terms of the different species included in the mixture change over time? And then lastly, but most importantly, is there one system that will be crowned king, or will it be a democracy? So for the current systems research, we're taking a farmlet approach, and we have 4 5-hectare farmlets, each allocated a different pasture system based on the pasture type. So the first system is a traditional Kikuyu ryegrass system. The second system is a plantain red clover fescue system. The pastures were established in 2019 by spraying off the entire area and then no-tilling the mixture in. The third system is what we refer to as a monoculture system, where the entire area was also sprayed off in 2019, and then a proportion of it was planted to a fescue monoculture, and the rest of it planted to a plantain monoculture. A fourth system was brought into the research during year 2, and this was a plantain, chicory, lucerne, ryegrass mixture, which was also planted using no-till methods into a sprayed-off area. It should be noted that the Kikuyu ryegrass system is oversown on an annual basis, while our other 3 systems with the forage herbs are not oversown on an annual basis, and it was decided not to oversow them at all during year 1. Each farmlet is also allocated its own mini herd of animals, and what we aim to do with these mini herds is to mimic a typical non-seasonal calving pasture-based herd in the system. And what this entails is that we have about 20 to 25 animals in milk, 5 dry animals. We aim to maintain an even distribution of lactation number and days in milk at approximately 150. And this means that we have a constant flow of animals into and out of the system. And then finally, each animal gets 4 kilograms of concentrate per day, with fresh pasture allocated twice a day. So we are collecting a lot of data, and I would refer you to our booklet to look at that specifically in terms of materials and methods, but I really want to dive into the data and get some of the answers we've been looking for. So the first question I want to answer is, how will systems impact the yielding ability on a farm level? So the first set of data we're going to look at is grazing capacity in terms of cows per hectare, and also milk yield in terms of kilogram per cow per day on a monthly basis during the year 1. So the blue line is for our plantain fescue clover mixture, the red line is for our monoculture system, and the yellow line is for our kikuyu ryegrass system. So firstly, going to grazing capacity, you'll see that during the winter of year 1, the grazing capacity was relatively similar between the two systems. However, as we move on to spring, we see that from middle spring almost to midsummer, our mixture system has a relatively higher grazing capacity than the other two systems, whilst our monoculture system has a slightly more favorable grazing capacity during midsummer. And then from late summer through to autumn, we see that the highest grazing capacity is indeed for our kikuyu ryegrass system. But what happens in terms of milk yield? So once again, you'll see that there are relatively small differences during the winter months and also early spring. However, from mid-spring through to autumn, we see that the milk yield obtained per cow is actually higher in the mixture system than for the kikuyu ryegrass or the monoculture system. When we look at the same data set for year 2 for the different systems, we now see that from basically early spring to mid-spring, the grazing capacity is favorable in our kikuyu ryegrass system. From mid-spring through to late spring, we see that it is then highest in our lucerne herb mixture. But again, the highest grazing capacity is maintained by the kikuyu ryegrass system from late spring through to autumn. However, when we turn to milk yield per cow, we see that it is highest for the mixture from winter through to basically mid-spring. There's a short period during the spring when the milk yield is higher for the monoculture system than for other systems. But again, from early summer through to middle summer, we see that the milk yield is then higher per cow for our mixture system. And then it's higher from late summer through to autumn for our lucerne herb mix. So as I move on to my next slide, I would like to kind of discuss how we typically represent data from pasture-based dairy research. So here we have a very popular method of doing it, and that's in terms of total pasture yield per hectare. And here you have it both on a seasonal basis, and then you can also see a comparison of the total over a specific year. And when you look at this data from this system trial, you'll see that during year 1, the highest total annual pasture yield was for our fescue plantain mixture system, and during year 2, it was for our kikuyu ryegrass system. Moving on, another traditional way to compare systems is to look at total milk yield per hectare. Now here, we're basically just combining the grazing capacity within a particular season with the milk yield within a particular season to get the total milk yield per hectare. And once again, it's highest for our fescue plantain mixture in year 1 and highest for our kikuyu ryegrass system in year 2. However, do we as pasture scientists and producers need to rethink how we're using systems research data to make decisions on farm? The thing is that farms are stocked at a constant stocking rate, so they don't have the luxury or the option to vary their stocking rate according to seasonal changes in grazing capacity. For this reason, we need to look at the yielding ability on a whole farm basis at a fixed stocking rate and a fixed area in terms of milk and pasture. We also need to consider how the system will affect fodder flow, so how much conserved feed will have to be fed during different seasons, and how much feed can we actually produce on farm to reduce the need to bring feed in from outside. The second thing that we need to remember is that grazing capacity also affects whole farm concentrate consumption. So could we reduce concentrate consumption on the farm by increasing our milk yield per animal and reducing our grazing capacity? And then lastly, how will the system affect the utilization efficiency of things like concentrate in terms of grams of concentrate used per kilograms of milk, but also nutrient utilization efficiency, for example, the kilograms of dry matter produced by kilograms of nitrogen applied to the area. So based on these challenges, I decided to look at what would happen if we have, for example, a 300 hectare farm allocated to a particular system, and you then stock that particular farm at an optimum stocking rate according to 2 years of data from the system trial. So our monoculture farm would then, at a stocking rate of 3.58 cows per hectare, have about 1,070 cows in herd. The fescue plantain red clover farm would have a stocking rate of 3.84 cows per hectare, and that would equate to about 1,150 cows in the herd. And then our Kikuyu Ryegrass system or farm would be stocked at 4.93 cows per hectare and have approximately 1,320 cows in the herd. Then, for interest's sake, I decided I was going to do a combined farm. So the combined farm basically means that a third of the area was allocated to each system. So a third of your farm, or 100 hectares, would be planted to the monoculture, a third would be planted to the mixture, and a third would be planted to Kikuyu Ryegrass. And your stocking rate would be 3.9 cows per hectare, and you would have 1,170 cows in that herd. What we did then was I took the farmlet study data consisting of pasture yield, grazing intervals, and milk yield, and then we used that data to calculate certain parameters on a whole 300 hectare farm for each system. So the parameters we calculated included pasture yield in tons dry matter per year, also milk yield in tons dry matter per year, pasture conserved in terms of dry matter per year, conserved feed required, the nitrogen applied on that entire farm in terms of tons dry matter per year, then also the total concentrate fed on that farm, that's tons dry matter, tons per year, and then we also looked at efficiency parameters like nitrogen use efficiency and concentrate use efficiency. Now, because that's such a whole lot of data, I then went and I normalized that data to give us index values. Now, these index values are simply aimed at making the data a bit more palatable. So for a favorable parameter, for example, pasture yield, which we want it to be high, you would take the other values divided by the highest. And for an unfavorable parameter, like for example having to feed conserved feed, you would take the others divided by the lowest. Now that all sounds very complicated, but I'm just going to quickly show you how I came to the end of the index values. Okay, so I know this table looks extremely intimidating, but what it basically comes down to is the second step I mentioned in the previous slide. So here you have your monoculture farm, your mixture farm, your Kikuyu Ryegrass farm, and your combined farm. Then you have numerous parameters calculated from the data from the systems trial, and that's for year 1 and year 2. Now, if you then go and you select the most favorable value for each of those parameters within a specific year, it's going to look as follows. So the most favorable value is highlighted. So for example, for year 1, in terms of pasture yield, the most favorable value was for the mixture. What you would then do to get to your index values is you would take, for example, that value and divide it by the highest value. And you would do that for all of the systems. Now, the reason I did that is that you can see there's no one system that does well in terms of all the parameters. And that's where normalization comes in. It just gives us a really good snapshot of how they compare overall as a system. So that then gives you your index values. So this is the index values for year 1 from 2019 to 2020. And here you have the different systems, the monoculture, the mix, the kikuyu ryegrass, and the combined system. And what you basically see is that when you sum all of the individual parameter index numbers, the most favorable systems was the monoculture and the mix. And what's interesting is that in year 1, this was primarily attributed to the fact that you didn't have to feed your animals as much, so pasture yield more closely matched pasture requirement, but also that you could still conserve a lot of the pasture yield on farm, which is a good characteristic. And then just interestingly that the kikuyu ryegrass system had the lowest index value during year 1. When you look at year 2, we see that the highest index values are for the monoculture system again, and then the combined system had a higher index value than both the mix and kikuyu ryegrass. Once again, for the monoculture system, it had the highest index value for having to feed animals. So that means that our animals were well supplied by the pasture available on the farm. So we didn't have to feed them as much as on the other systems. And then also it had a relatively high conserved fodder. So aside from the fact that we don't have to feed them as much, we're also conserving a lot of pasture on farm. In terms of this, just interestingly enough, the combined system also had a higher rate of feed conservation on the farm. So we were making a lot of bales compared to, for example, the mixed system. And then just interestingly that during year 2, the mixed system had the lowest index value, whereas, for example, it had a relatively okay index value in year 1. So that just shows the vagaries of how a system can perform well in 1 year and then do poorly in the next year. So the next question I want to look at is how do these systems change over time, specifically in terms of botanical composition. Okay, so one of our big hopes is that bringing these species into the systems could improve the contribution of the sown species, particularly over time. So could improved persistence mean that we don't have to oversow on an annual basis? So on this graph, we have the contribution of the sown species. So for a fescue monoculture, a plantain monoculture, and then for a fescue plantain red clover mixture, and then also for lucerne herb ryegrass mixture. And then finally for the kikuyu ryegrass system, I'm only focusing on the ryegrass component because that's something we have to actually establish every time. So what was interesting is that firstly, it did clearly show that the ryegrass contribution declined rapidly in summer, which definitely indicates that we need to oversow that on an annual basis to maintain the ryegrass content in our pastures. The second thing, which was quite interesting, so the blue line is our fescue monoculture, and then both of these, or all these lines above, have some form of herb included in them. And that just kind of highlights the fact that in the absence of herbs, you are likely seeing a lot more weeds in those pastures, and most of those weeds are actually grass weeds. So could forage herbs be the answer to reducing weedy grasses in our systems? So the next graph I want to discuss is aimed at determining how would botanical composition within the mixture change over time. So here we're looking at the fescue plantain red clover mixture in terms of botanical composition, and each line represents a different component. So the blue is the plantain component, the green is the clover component, the black is the weeds, and the green is the legume or the red clover. So the most interesting trends here was that it was quite obvious that the red clover increased notably from spring through to summer in the first year. However, at about in January, its contribution then declined, and it remained relatively low from autumn onwards in that system, showing that the red clover is likely to not be as persistent as we would like in the system after year one. The second interesting thing is that as the clover declined, the plantain actually increased in terms of contribution from about middle summer through to autumn, and we then found that the botanical composition kind of stabilized after summer of year one. And what was a bit concerning is that the grass actually made a relatively low contribution at less than 20%. So in the second year, we decided to include another pasture treatment, and that was a mixture based on lucerne, chicory, plantain, and ryegrass. And this graph just simply shows the change in botanical composition of that mixture over time. So the black bars is for the ryegrass, the red is for the chicory, the green is the contribution of lucerne, and then the blue is the contribution of the plantain. So what we found is that from winter through to late spring, the ryegrass was definitely the major component in this mixture. However, at the end of spring, the ryegrass contribution dropped quite dramatically, and that was associated with an increase in the chicory component. And then what was quite interesting is that by the time we went into the second winter, you'll see that the contribution of each of the components, the plantain, the chicory, the lucerne, and the ryegrass, was quite balanced. So what can we take away from this presentation, or from the data we've collected thus far from the system trials? Well, the first is that a whole farm analysis is definitely required to determine how productivity on a farm level will be affected by the different pasture systems. And that within our current systems, the ability to produce food on farm is a major driver in the productivity of the system. So the more on-farm feed we can get into our animals, the better. The second is that the inclusion of forage herbs can reduce the need to oversow on an annual basis and lead to improvements in botanical composition of our pasture. And then lastly, the composition of pasture mixtures can change dramatically over time depending on the species included. And with that, I would like to thank you, and please feel free to contact me if you have any questions.
The presentation is about partial replacement of perennial ryegrass with plantain when feeding either a low or a high level of concentrate to Jersey cows in spring. Plantain has become more popular in the Southern Cape over the past few years, and the reasons are obvious. Firstly, it's more drought resistant than ryegrass. It's got a deeper root system. It can out-yield ryegrass, especially during winter. Then it's got a higher quality than kikuyu, and hopefully will increase milk production when incorporated into the system. So how do farmers use plantain in their pasture systems? One way to use it is as a pure sward, where they graze plantain with cows during the day and ryegrass during the night, or either in a pasture mix. And there are quite a few options, either ryegrass and plantain, some red clover, lucerne, chicory, and there are different combinations using these crops. The nutritional value of plantain has been well documented. This is a specific study where they showed crude protein similar to that of ryegrass, NDF content lower, and sugar content slightly higher, and then also increased milk production. The question, however, is what will happen with effective fiber if a substantial part of the diet becomes plantain instead of ryegrass. The aim of the study is to determine the effect of partial replacement of ryegrass pasture with plantain pasture during spring and on milk production and milk composition of cows fed either a low or a high level of concentrate. So we asked the following questions. Will partial replacement of ryegrass with plantain increase milk production? Will it decrease milk fat? Will it increase protein content? And how will it affect the response on concentrate feeding? The treatments are as follows. Treatment 1, cows graze ryegrass during the day and during the night, and they are fed 3.5 kilogram of concentrate. Treatment 2, again ryegrass day and night, but then 7 kilogram of concentrate per cow per day. Then we get to treatment 3, plantain during the day, ryegrass during the night at the low level of concentrate feeding of 3.5 kilograms. And then treatment 4, again plantain during the day, ryegrass at night, and then 7 kilogram of concentrate. The composition of the concentrate fed, the dairy concentrate fed on an as-is basis was 12% protein and 11 megajoules ME per kilogram as is, and then calcium 1%, phosphorus 0.4%. The design was a factorial design with 60 cows and 15 cows per treatment. Cows were then blocked according to milk production, days in milk, and lactation number. We had a 15-day adaptation period followed by a 45-day measurement period, and our study started September 2020 to the 31st of October 2020. Cows were milked in our dairy parlour, 20-point swing over dairy parlour, and concentrates were fed in the dairy parlour at 3.5 or 7 kilogram per cow per day. So this was then divided in 2 portions. We measured milk production daily, milk composition 4 times every second week during the measurement period to determine fat, protein, lactose, milk urea nitrogen, and somatic cell count. Live weight and condition score was determined at the start and the end of the study. And then concentrate and pasture samples were collected weekly and pooled for every 2 weeks, and then analyzed all those parameters that are listed there. So it was a factorial design where we had pasture as one factor, which was then Kikuyu ryegrass, or Kikuyu ryegrass and plantain, and the concentrate was then the other factor at 2 different levels. The statistical analysis was done using SAS, and then significant difference were declared when the p-value was smaller than 0.05. In table 2, the composition of ryegrass and plantain as well as that of concentrate is presented. Dry matter content of ryegrass and plantain was both quite low at around 12%. The crude protein content of ryegrass was 19.8, whilst plantain only contained 13.6% protein. This is much lower than we expected. The ME value is above 9 for both pastures, and then the concentrate ME value of 11.4. The NDF content of ryegrass was 47.9 and that of plantain was 38. This is substantially higher than we expected. The calcium content of plantain was 1.38%, which is much higher than that found for ryegrass. In table 3, we show the results on milk production, milk composition, and live weight gain. Here we present the main effect of pasture treatment, as there was no interaction between pasture treatment and concentrate level. So for cows on ryegrass during the day and night over the concentrate treatments, average milk production was 18.8. This went then up to 19.4, but was not significant. Fat-corrected milk did not differ between the pasture treatments. Milk fat was similar. Milk protein also similar. No difference in milk lactose. The milk urea nitrogen level was 9.1 for the ryegrass, and only 5.8 for ryegrass plantain. This indicates a potential deficiency in protein due to the lower protein level that was found in the plantain. Live weight gain was similar. Both groups gained substantial weight during the experimental period. When looking at the effect of concentrate treatment, feeding either 3.5 or 7 kg of concentrate, milk production increased from 18.4 to 19.8. It was significant, but very disappointing, as this was only 1.4 liter more milk for another 3.5 kg of concentrate fed. Fat-corrected milk also increased in a similar way. Milk fat percentage did not differ. Milk protein was similar. Milk lactose percentage was similar. The milk urea nitrogen level was sufficient for the 3.8, the 3.5 kilogram of concentrate feeding, but slightly marginal for the 7 kilogram of concentrate feeding. Live weight gain again was similar, indicating that cows that got a lower level of concentrate still gained weight. Now, when looking at the economic implications of the study, especially focusing on the concentrate feeding side, to get 1.4 kilogram of milk for an input of another 3.5 kilogram of concentrate is disappointing. So the return was only 0.4 kilogram of milk per kilogram of concentrate fed. When we assume that pasture costs R1.50 and concentrate R5.80 and the milk price is R6.20, we can do a quick calculation. Using the milk data, milk income differs slightly, but the cost of concentrate feeding was substantially, of course, more when we fed more concentrate. We estimated pasture intake at 10 for the 3.5 kilogram concentrate level and 8 kilogram pasture intake where we fed more concentrate. And then calculating the costs, we in the end get to a margin over feed cost. So the interesting part is that the margin over feed cost increased by R9.62 per cow per day when we fed less concentrate compared to more concentrate. So the increase in margin rand per month for a 400 cow unit would be in the order of 115,000 rand, which is quite substantial. So with this, we want to really encourage farmers to look at response on concentrate feeding and to consider feeding lower levels of concentrate when pasture quality is high and pasture availability is also high. So a few conclusions. Partial replacement of ryegrass with plantain in spring did not affect milk production or milk composition. Then increasing the concentrate from 3.5 to 7 kilogram per cow per day did increase milk production. However, response was poor at only 0.4 kilogram of milk per kilogram of concentrate. And then, yes, when pasture quality and availability is high, be very critical of feeding high levels of concentrate and consider feeding less. Thank you very much. This presentation is about milk flocculation, and the question we do ask is, does feeding more phosphorus to cows improve milk protein stability? UHT milk is well known to all of us, and this is where milk is exposed to a high temperature between 137 to 150 degrees centigrade for 1 or more seconds, and this milk is then processed as UHT, and now it lasts for a long time and be stored for a long time, even not being in a fridge. However, one of the problems experienced with UHT milk is the stability of the protein in that milk after exposure to that high temperature. When you look where the arrow is showing there, you can see small parts of milk. We call it flocculation, and this is basically coagulation of milk protein. When this happens, it's a big problem, and to monitor this, milk is being tested with a Lizerol test, which is an alcohol test, and milk has to pass this 76% Lizerol test to make it suitable for processing as UHT. Industry has been struggling with problem of poor stability of milk protein, especially during times of heat stress, as we experience in autumn, like March, April. Also, nutritional stress on cows adds to this problem. Another factor that has been seen in the past, that if we underfeed protein and the milk urea nitrogen is low, we will have a higher incidence of milk flocculation. The previous study has also showed where the diet is high in potash, the milk tends to be less stable. In literature, we can clearly see that if there's ionic calcium available or free calcium in the milk, this causes a problem with increased flocculation. Then low levels of phosphorus can also be a problem, and if the milk contains more than 1% minerals, often it also will be an indication of problems. To understand this better, we have to just have a quick look at what's happening with the protein. And the protein is organized in casein micelles. These micelles are divided in submicelles, and very important there are calcium and phosphate linkages between those. And if we see this whole casein micelle, it's important to note that it is negatively charged. So these micelles repel each other, so they push each other away. So it's obvious that if we do have cations, like loose calciums in between, we can cause coagulation of milk. Several approaches have been used in the past. One of them was supplementing monocalcium phosphate to cows to increase the phosphate feeding to cows. Supplement urea. It has been shown that milk with a lower MPN content is less stable. Feeding more concentrates has helped to a certain extent. And we definitely do find more unstable milk during periods of heat stress. And to link with this, Sanchez done a study where they determined that the supply of phosphorus to the udder was reduced by 50% during heat stress, so creating a problem with availability of phosphorus. And unstable milk contained lower levels of phosphorus in the study of Fagnani. So the aim of our study was to determine if changing the calcium-phosphorus ratio in the diet of cows grazing Kikuyu ryegrass pasture in late summer, changing that ratio from 2:1 to a 1:1 ratio, but it doesn't mean that we reduce the calcium now, it just increase the phosphorus. And if this will now improve the protein stability of milk. Materials and methods. We used 80 cows in a crossover design with 2 treatments. First treatment, dietary calcium phosphorus ratio of 2:1, and second treatment, calcium phosphorus ratio of 1:1. Cows grazed Kikuyu ryegrass pasture during February and March 2021. We had an adaptation period of 2 weeks and a measurement period of 1 week. During this 1 week, the composite milk sample was taken on Monday, Wednesday, and again on Friday. These samples were then analyzed for milk fat, protein, lactose, MUN, and somatic cell count, as well as doing the alizarin test at 72, 74, and up to 80% alizarin. Then milk minerals were analyzed: calcium, phosphorus, magnesium, potash, and sodium. Concentrates fed to cows, typically maize-based concentrate with soybean oil cake as a protein source. Important to note that the higher level of monocalcium phosphate fed in the high P concentrate. So that's what we use to increase the phosphorus in the concentrate. The composition of these concentrates is shown in table 1b. ME value around 12, crude protein 15, NDF 16, calcium 1.2, and then the phosphorus for the control only 0.4 9, whilst on the high P concentrate 1.18% of phosphorus. When analyzing the different concentrates in the pasture that the cows consumed, this is what we got in table 2. Crude protein of the concentrate, control concentrate 13.6 going and 14.4 for the high P concentrate. Actually should have been exactly the same. Pasture 22.7, so this was not a bad quality pasture with a relatively high protein content. ME value 12.4. In the F of the pasture 51.2, so also showing relatively good quality pasture. But then the important one is the calcium content of concentrates 1.39 and 1.3 for relatively the control and the high P, and then on the pasture only 0.44% calcium, and then the high phosphorus concentrate did contain a high level of phosphorus at 1.22%, as we wanted to achieve, and the pasture only contained 0.49% phosphorus. So the results of the alizarin test is shown in table 3. We can see the different levels of alizarin tested from 72 to 80. And what is shown there is the percentage of cows that failed the specific test. So at 72% alizarin, 12% of the cows failed the test, so milk flocculated of those cows, and only 9.9% of the phosphorus treatment, but the difference was not significant. Then the same goes for 74%, about 20% of cows not making the test, failing the test, and then 76%, up to a third roughly of cows failed the 76%. Now this is important because this is the level you should achieve to make milk usable for processing as UHT. So we still had a major problem with flocculation, although no difference between the control and the high phosphorus treatment. Looking at milk production and milk composition, no difference in milk production, 16.6 and 16.7. Fat corrected milk, no difference. Fat percentage, no difference. Milk protein, there was significant difference, but that difference is so small that it doesn't have any practical value. The reason why we do find a significant difference is because very little variation in milk protein was found. Then lactose also the same. Milk urea nitrogen indicates that protein was not limiting. So we do have enough protein, and there was no difference between the two treatments. Somatic cell count was actually good, so no problem with milk hygiene or high somatic cell count. Then milk pH, also showing no problem with acidity. And then the average level of alizarin passed, 76.5% for the control and 76.4%, no difference. So we did not move the stability of milk in the right direction by adding more phosphorus. Looking at the mineral composition of milk of cows under the specific treatments, interesting to note that these values are in line with what is reported in literature, and they have found that if the phosphorus content is like 50 milligrams per 100 ml, then milk might be unstable. In our study, the levels were high enough with no difference between these minerals shown between the control and the high P treatment. So to make a conclusion is, in our study, increasing the phosphorus and did not improve protein stability of milk. It did not change mineral content of milk. However, a third of the cows still failed the 76% alizarin test. So we still had a problem with stability of milk, although there was no nutritional or heat stress, and the milk had a normal mineral content. So what now? So this is specifically a case where supplementation of phosphorus did not really help. We have to look maybe at the genetic base. and identify cows in the herd with unstable milk. Interesting to note that when we tested individual cows of the whole herd, individual cows, it was often found that out of 250 cows, 50 of them would have unstable milk, and they also tend to repeat. So they stay producing, keep on producing unstable milk. We have to say that still undersupplying of phosphorus will aggravate the problem of flocculation. An oversupply of potash will still increase the problem of flocculation. I just would like to acknowledge Milk SA for financial support and Clover for supplying consumables that we used in the study, also the Western Cape Agriculture Research Trust. Thank you very much.